Hello, everyone, and welcome to this seminar. I'm going to talk about Kriging, which is a method of spatial interpolation. I'm going to talk about some of its applications, its methodology, and how to implement it. So, the initial challenge that gave way to modern interpolation methods goes back 3,000 years ago, and it comes from a mining background. What you're seeing in this picture is called the Turin Papyrus, which is the oldest surviving geological map. It's a map of mineralization and types of rock in a geological setting. It was trying to set directions for miners to follow to mine the material that they were looking for. This is the oldest example of not just geological maps, but also interpolation efforts, because clearly the people who wrote this map and who drew this map, they didn't have observations at the entire region that they draw the map based on. Of course, they had very few samples and observations, but they made guesses, they made estimations of the content of the subsurface, of the content of that region based on those few samples. That is the essence of spatial interpolation. And as you can see, it's a very old challenge. So coming to the modern times, the challenge is still going on. We're still trying to make spatial interpolations of variables at different domains. For instance, in this conceptual example, we have 5 samples of a variable at space, and we're trying to make estimations of that variable at the entire domain. Of course, we can't make estimations in an infinite number of points, so we discretize our domain by equally volumed cells. We call this the grid network. So we make estimations at those grid locations, but we only use those 5 samples. That is the essence and the general framework of spatial interpolation. And since then, many new applications have been found for spatial interpolation. Of course, one would be mining. In this case, this is a mineral deposit. We're trying to interpolate values of a mineral grade at that setting. But there are also other applications. For instance, this is a global map of temperatures around the world. And this is also a result of spatial interpolation. Of course, there are finite samples of the world's temperature at different locations, but this map illustrates temperatures everywhere. That is also a case of spatial interpolation. But of course, the major applications are still in earth sciences, in mining and petroleum, and that will be the focus of our seminar too. So now that we know what interpolation is, and more specifically spatial interpolation is, and what its applications are, we're going to talk about the methodology of Kriging, which is one of the most widely used methods of spatial interpolation, especially in case of earth sciences. So before talking about Kriging itself, I'm going to talk about linear regression, because as you will see, Kriging is just an extension of linear regression, um, and it uses the same equations with very few differences. So in a linear regression set, we have 2 variables, z1 and z2, and we know that they are correlated with one another. And the question is, can we make estimations of z1 using values of z2? And by defining the error of such estimations, which are z1 star, we arrive at this equation, which is the equation of simple linear regression. And it says that estimations of z1 can be defined by adding these, which needs the mean of z1, the mean of z2, and this coefficient, which comes from the standard deviation of z1 and z2 and their correlation. This is simple linear regression, 2 variables. We can, of course, have many more variables. The equation is practically the same, but we have more arguments in this place. But we also need a different approach to find these coefficients. We can find those coefficients using the variance covariance matrix. So imagine if we have n variables that we're trying to use them to make a regression of our variable of interest, which in this slide is defined as z0. So if we put the covariances between all the n variables together in a matrix, it will look something like this. Of course, the diagonal of that matrix will be the variances of the variable, and the other cells are filled with the covariances. We can find those coefficients in multiple linear regression using this equation. Of course, this is the variance-covariance matrix that we defined here, and this is the covariance between the n variables and the regressed variable, which is in this slide z0. Solving that equation gives us these coefficients, and that's it. That's multiple linear regression. But just imagine in multiple linear regression that those n variables that I talked about, instead of just any random variable, these were values of samples of one spatial variable at a spatial setting. And our regressed value, or z0, is a regression or an estimation of that same spatial variable at one unknown location. By making those assumptions, the problem of multiple linear regression has just turned into the problem of Kriging. And that's the only difference between them. It's the same equations. The only difference is that now we're talking about the same variable, for instance, let's say copper grade. Uh, but we have different samples or n samples of that variable, and we're trying to make estimations of copper grade at the entire subsurface using those n samples. That is the problem of Kriging. It's the same equations, it's the same approach. There are a few assumptions behind Kriging that I will go through very quickly. If you go back to the formula for multiple linear regression, you will see that we have different means for different variables. Of course, in Kriging, we have the same variable at different locations. So in order to be able to conduct kriging, we need to assume that the mean of that variable is the same for the entire subsurface. That means that all our n variables and our regressed variable has the same constant mean. It also has the same constant variance because the diagonal in the variance-covariance matrix consists of variances of the n variables, and they are the same variable at different locations. We also need them to be the same. And finally, and probably the most important of the assumptions, is that the correlation between each pair of points at space is defined by the variogram and is only a function of their distance vector. So if you remember the variance-covariance matrix, we had covariances between our variables. Of course, we know how to find a covariance. But now that we have defined that those n variables are samples of the same variable, how do we define the covariance between them? That covariance is defined by something that we call the variogram. We will go through them in the next slides. And it is important that there is an assumption behind that. And that means that the only factor important in the correlation between points in space is their distance vector, is how they are distanced from one another. Okay, now that we have defined kriging, let's talk about the variogram, which will give us the correlation between points at space and will be used as input in the variance-covariance matrix and will give us the covariances that are needed to conduct kriging and fill the Kriging equations. So let's take this setting as an example. There are samples of porosity at a 2D setting, and we ask the question that let's pair points that are distanced 4 meters from one another, and let's do that along roughly this direction. So we start by here, we will look for points that are distanced 4 meters from one another, and we pair them. And we plot the results in this scatter plot that you can see here. Of course, there is a correlation, in this case a negative correlation between these points. We call this an H scatter plot. So this plot represents all those pairs that we just found here. Of course, many more of them. It is conceptual. But yeah, that's the whole point. Plot them together and let's proceed. So now that we have that plot, we have all the pairs that are distance 4 meters in our example from one another. We go on and use their values to find the variogram. This is called the variogram, and this is the expression to calculate it. So for instance, let's say at the lag distance of h equals 4, we have found all pairs of points that are distance 4 meters from one another. So we find the average squared distances between all those points that are distance 4 meters from one another, and we define that as the variogram for the distance of 4 meters. So that distance could be anything. It could be 1 to 20 meters depending on the size of our domain. So we go on and calculate the scatter plot for all the points that are distance h meters from one another, and then we calculate the average square distance for all those different scatter plots, and we end up with different variogram values for different points. And that's how we end up with the experimental variogram. What you see here is called the experimental variogram. As you can see, we found these points, the values of these points from this equation, and each of those points represent a different scatter plot. These are all points that are distance this many meters from one another. These are points that are distance this many meters from one another. Plotting these points gives us what we call the experimental variogram. As you can see, the points that are distanced closer to one another, as you can see in the scatter plot, are, of course, much more correlated with one another. But again, that's what we expect. These are points that are closer to one another. And the geological processes that formed these rocks and these minerals and these samples, they are more similar. Of course, we can see that in our scatter plot too. But as we increase the lag distance and we're looking at pairs of points that are distanced more and further away from one another, that correlation fades away. And that's the whole point, that the variogram captures the reverse of that. By increasing the distance, the variogram value increases. Of course, we expected that as well. That's the average square difference. So the difference increases and the correlation drops. In any case, that is the basis of finding the correlation of points in space, the experimental variogram. Um, so in the two slides before that I talked about pairing points at a specific direction, that direction I didn't discuss how we ended up with that direction. That direction comes from a concept called anisotropy. So let's start by this example. Let's say there is a factory here that is producing pollutants, and we are mapping those pollutants in the air. Of course, if there is no wind, all those pollutants are, roughly located around the factory. But if there is a wind in this direction, we can clearly see that the pollutants are spread much more along this direction than at any other direction. So that means that there is anisotropy in the amount of pollutants in that direction compared to other directions. If you look at this direction, you can see more continuity. There are more pollutants in that direction. But if you look at them in this direction or in this direction, you might see some pollutants at this part, but you don't see any more here. So that's the basic concept of anisotropy. Of course, in this case, there is a valley, and the pollutants are seen along the valley because that's where the wind will blow. Imagine if instead of wind, we had geological processes that laid, but instead of pollutants, minerals in specific directions. Of course, the directions that we will see more continuity in those directions, those are directions that we say are anisotropic in that specific direction. Lots of directions to talk about. So that's how we define the major direction of continuity. That is the first decision we make in modeling the variogram. The major direction of continuity is a geological understanding. It comes from geological understanding. And we say, based on the geological understanding of the region, that in what specific direction there is more continuity. So it's usually an input. We don't usually define that in the process of kriging. And that's the direction that we start picking pairs of points along that direction, because that's the direction we're expecting to see highest levels of continuity in terms of our variable, whatever that variable is. And the minor direction is, in context of kriging, the minor direction of continuity is automatically defined perpendicular to the major direction. We'll talk more about that in the next slides. So if you remember in the first slide that we talked about the variogram, I defined that we are looking for pairs of points that are distance 4 meters from one another in a very specific direction. But if you have a finite number of samples, defining the direction to look for samples to be that, concrete and say only that specific direction and only 4 meters, you will probably end up with very few samples to model your variogram and to plot your variogram. And that's not a good thing. So in order to, have more samples that are paired together, we define tolerance parameters, which you can see in this picture. So for instance, we say, okay, we're trying to pair this point with another point, but instead of saying it has to be 4 meters away exactly at this direction, which would only give us points here, we say, okay, look for points in all this area. So we have an angle tolerance, which says, okay, look in that direction, but also accept plus or minus 10 or 15 degrees as well. And we say, okay, look for 4 meters, but also accept 4 minus 1 plus 1 meters as well. So those are defined in order to find more pairs of points that will help stabilize our variogram. So the initial challenge of Kriging was to estimate values of a variable at the entire domain, at every single location. If you go back to the variance-covariance matrix, you can see that if we have n number of samples, we need correlation between all those samples and every single location at the domain. And we have to find that correlation to come from the variogram. But our variogram that we defined in the previous slides, and we called it the experimental variogram, it only gave us the value of the variogram at specific lengths and at specific distances. So if we have plotted our variogram every 1 meter, and we're looking for points that are paired 0.76 meters, there is no value in our variogram for that distance. Even more, we have only found the variogram in one or two directions, the major and minor direction of continuity. But we need that in every direction because the distances we're talking about isn't just a scalar distance, it's a vector. So if 2 points are distance h meters from one another, there's actually a vector of h that has a distance of h and a specific direction that pairs those 2 points. That issue means that we need a much more comprehensive variogram model. We need to have models that points at everything in our domain and gives us values for our variogram at any distances of h at any direction. That challenge leads us to variogram modeling, which is the process of fitting some known variogram models that you can see 4 of them here into our experimental variogram. And finding the best fit gives us a model that will give us values of our variogram at every location. And that enables us to actually do Kriging for the entire domain. So you can see 4 of the most famous ones. The nugget effect is just basically a constant value. The spherical, the exponential, and the Gaussian are 3 others. Their shape is what defines them. And we're trying to look for the best fit into our experimental variogram, which is something we'll talk in the next slide about. The result of variogram modeling is something called the nested structure. The nested structure is a combination of different known variogram models, that 4 of them were depicted in the last slide, with different specifications in a way that their combination fit the experimental variograms that we have produced the best. For instance, in this example that you can see, this is from the lab material. So the blue points are the experimental variogram points along the 35-degree azimuth, and the red points are along the 125-degree azimuth. So you can see that they are perpendicular to each other. The blue ones are along the major direction of anisotropy, and the red ones are along the minor direction of anisotropy. That's usually the 2 directions that we plot the experimental variogram in those directions, and then we do the variogram modeling using those points. So we have these experimental points, and those lines, they are the variogram model. So where do they come from? In this case, this is the variogram model, or the nested structure that is defined for this variogram. We're going to go through the properties that you see here and how they define the variogram model. So we talked about the nugget effect and the exponential structure in the last slide, and we're going to see how their combination is going to shape the variogram model that you see here. For instance, we have nugget effect with a CIL of 0.4 and an exponential with a CIL of 0.6. So what do these CILs point towards? It would be an appropriate place to talk about the variogram CIL in general. So if you have looked closely to the variogram plots that has been shown up to here, there's always a line, a horizontal line at 1 in every variogram model. This is what we call the variogram CIL, and it's not supposed to be actually 1, it's supposed to be the variance of the variable. But it's 1 because we usually standardize the variance to be 1 in order to make it more easy to interpret our data. But that's supposed to be the variance, and it's supposed to say that experimental points that reach this horizontal line or reaches the CIL are so far distanced from one another that their average squared distance is actually the variance of the variable. So they are not correlated to one another at all. That is the point that all spatial correlation practically stops. And even if we have experimental variogram points that go beyond the CIL, we don't even try to model them. In our variogram model, we only pay attention to those points that are below the CIL. So that's something to note and to think about. And what you see here in terms of the CIL for each of these structures is how much of that one CIL that we have plotted here is explained by each of these structures. For instance, here we only have two structures. And for instance, the nugget effect has a CIL of 0.4. And almost always, the nugget effect has a range of 0, which practically means that you don't see it in the model. You don't see any horizontal blue or red line, because that means that the 0 range makes the model starts from 0.4, but it doesn't result in the nugget effect to be shown in the model. So that's something to remember, that the nugget effect is always used to push the variogram model to start from a point, not 0. And that's useful because sometimes we have variogram structures that there is so much discontinuity at very short scales, and the nugget effect is used to explain that. And we also have the exponential, which has a CIL of 0.6. So this says that the nugget effect starts from 0.4, and the exponential has the rest of the 1 minus 0.4 or 0.6 of the variance explained. And it has a range. The range of each of these structures in the variogram model represents how long it would take for them to flatten out. So if you go to the previous slide, you can see that all these models flatten out after a point. The range defines that. So the higher the range, the higher distance it would take for that structure to flatten out. So we have a range of 800 here. You can, of course, change that range in R and see if the model is better fit. That is, of course, one of the parameters. So that's up to the modeler. That would be you and me to decide what that range would be. And there's also an angle, which is 35, which happens to be the major direction of anisotropy. So in R, we give the major direction as input to our structures, of course, not the nugget effect, but all other structures. And then we define this ratio called anisotropy. This means that, of course, the range in the major direction is supposed to be the longest because that is the direction we're seeing most continuity in. So it would only make sense for points to, have a more continuity, or better to say, take more distance to reach the CIL along that direction. So the distance or the range in the major direction is defined here, and a ratio is defined here, which would say, okay, how much higher in the minor direction, excuse me, uh, it would take for the variogram to reach the CIL. For instance, if the range is 800, it is bound to be less in the minor direction. An anisotropy of 0.5 makes that to be 400 meters. So, and a different ratio here would change that range. So that's a measure of saying we are seeing twice as much continuity in the major direction of anisotropy compared to the minor direction. And just to wrap this up, we have now the variogram model. We can actually do Kriging, but there's just one more thing to talk about, and that's two different approaches to Kriging, simple and ordinary Kriging. In simple Kriging, that is just the Kriging that we've been talking about. We assume a constant mean and we do Kriging. But in ordinary Kriging, we actually define the sum of the weights or the coefficients to be 1. And because of that, we don't actually need the mean. We don't even need to assume that it's constant, which is actually often the case. You can see how that happens here in this formula. By defining the sum of the coefficients to be 1, we end up with something like this, and it actually removes the mean from the Kriging equation. This is actually the regression equation, but you can see that it is removed, and so we no longer need it. And that's what we will be focusing on the lab, the ordinary Kriging, because it's more robust and it removes our need to a constant mean. And this is a result of ordinary Kriging. As you can see, we have done estimations at a domain. We have values of our variable everywhere. That was what we were looking for. That was what Kriging was all about. Thank you for listening and thank you for your time.